Molar solubility units, moles per liter, same deal, same, going to be using M or moles per liter here. Now let's look at the ratios again. Ratio of 1 to 1. The Ksp expression is always going to give you Ksp x equals x squared. Now, I gave you the generic. I'm not sure how far I got into this, but AB solid is going to break apart into A plus ion and B minus ion. We have the one formula unit here. This is a 1 to 1 ratio like that. So the one formula unit breaks apart into one of the cations and one of the anions. Very simply put there. Now we can do the K expression here for this one. It's going to be the concentration of the A times the concentration of the B. Because, you know, these are the AQs, so they would be part of the KP expression. So that means for however much this dissolves, a certain amount of A will dissolve in the water. And since it's 1 to 1, that means that will be the same number as the B. So that's why it's X times X. So this here, you would get Ksp equals X times X. And that's where ultimately this idea comes from. I'm sure I gave you some examples, but I'm going to write them over here just for everybody. Calcium carbonate's a good one. Silver chloride's a good one. The silver chloride, it's +1, -1 for the ions, and the calcium carbonate, it's +2, -2 for those ions. So that would be how the 1 to 1 ends up looking. For the 1 to 2, not sure if I showed you both scenarios or not, so I'm going to go ahead and make sure that I do so. The 4x to the third, probably showed you this one. Right here where it breaks apart into the A2 plus the 2 B minuses, right? That's one possible way of looking at a 1 to 2 ratio. 1023 was the number. Anyways, A to B. So here, this one is where the cation is the 1, and the cation is the 2, and the B is the 1 here. So we would get, not concentration, we would get 2 of the A pluses and 1 of the B minus 2s, like that. So there's 2 different scenarios for 1 to 2, like that. Doesn't really matter which one you're looking at, because every time this one formula unit breaks up, you're going to get 1 of these and 2 of the other. That means you'll get X of that and 2X of the B's there. On this side, every time this one formula unit breaks up, you're going to get 2X of this and X of that. And that's where those values really come from. Now, when we do the K expression, Ksp expression, okay, where we have A to the 2 plus and then B minus, this one has to be squared though, because of the 2 here. You plug these in, like so, Ksp ends up being X times 4X squared. Well, X times 4X squared gives you the 4X to the third. So that's going to be the same deal on the other side. It's just going to be the A gets squared and the B is just the X, and so forth. Now 2 examples for this one. An example that looks like this one over here is going to be the Ag2CO3. That's silver carbonate. One that looks like this one could be the copper hydroxide. copper 2 hydroxide. So different types of 2 to 1, 1 to 2, and how that looks. And where do we get that 4x to the third from? Well, this is how you would break it down. Now for the 1 to 3s, it gets more interesting. 1 to 3s give you 27x to the fourth always. Now why is that? Let's take a look and derive that out. We have our A3Bs. So we get 3 A pluses and 1 with the B minus 3 like that. Or we have the AB3 where we get A3 plus and 3 of the B minuses. Either way, you're going to end up getting a 1 ion to a 3 ion arrangement for every time that formula unit breaks apart. So I'm going to do this side this time. Let's write out the expression for this one. Concentration of A times the concentration of the B, but this time it's going to be cubed. And for every formula unit here that breaks apart, you're going to get 1 of these, 3 of these, so this is going to be X, and this would be 3X. So then we plug that in here, so we would do Ksp equals X times 3X cubed. And this, of course, gives you X times 27X to the third, because 3 cubed is 27, right? So that's where this comes from, that 27. And then the X times the X to the third gives us the X to the fourth there. So same thing would happen on this side, except for this would be the 3X, this would be the X. Still end up getting the 27X to the fourth as your way of calculating molar solubility. Couple of examples for this one. On this side, copper 1 phosphate. That would look like the one over here to the left. Over here to the right, aluminum hydroxide is a good example for this type of arrangement. The last fun ratio is 2 to 3 or 3 to 2. Well, guess what? It's Ksp 108 x to the fifth. This one's fun. This is super fun. All right, so our two possibilities here, we have the A2B3 solid. This one breaks apart into 2 of the A3 pluses and 3 of the B minus 2s. That's one scenario. Over on the other side, let's do the other one, which would be A3B2. So you get 3 of the A, why am I putting an L there? I don't know. This is going to be 2 pluses, and this would be 2 of the B3 minuses. So let's think about here, Ksp. Writing out that expression here, this is going to be, of course, A3 plus, but it's going to be squared now because of the 2. This one's going to be B minus 2, but it's going to be cubed. And if you look at the way this is going to happen, for every 1 formula unit of the crystal, you're going to get 2 times that value. Like for every one of these, you get 2 of the A's out of it, and you're going to get 3 of the B's out of it. On this side, it would be the same thing, except for the cation would be the 3x, and the anion would be the 2x. Either way, you plug it into the expression, this ends up being 2x squared, and this ends up being 3x to the third. And if you do the math on that, This is 4x squared times 27x to the third. And I bet you can probably estimate what 4 times 27 is. 4 times 27 is what? 108. That's where that comes from. Good. And the 2 times the 3 there for the x gives you the x to the 5th. That's where that comes from. A couple of examples for this one. An example for our A2B3 would be like iron 3 carbonate. Oh, sorry, that should be a 3, excuse me. There should be a 3. Iron 3 carbonate, that works for that side. Over here, an example of this 3:2 would be zinc phosphate, like so. So those are a couple of examples and where those KSP ratio numbers come from and why we are allowed to just use them that way. Because now we're going to do some problems where we use these and we figure out molar solubility and we can calculate KSP and stuff. So this is the basic of the basic KSP problems. You're basically taking the salt and you're dumping it into a beaker of water. And you want to dump it in there until it reaches equilibrium and it's saturated and you can't dump any more in there. And you want to know what that molarity happens to be, because that's the molar solubility or the solubility. Now, it doesn't say it in here, but you can assume any of the KSPs I give you are going to be at 25 degrees Celsius, which is standard conditions. Because those are the ones that are in the tables. Now, the way to set this up, going to show you the actual steps of the modified rice chart, although once you see it once or twice, you don't really need to write it down. So you get the idea. So start out with your rice. Our reaction is for silver chloride, dissolving. This is dissolving, so we get Ag plus and RCl minus, which is VAQ. Now initially, you're dumping it in there. You have no ions initially to start with, so this would be 0. This would be 0. And since the solids are not accounted for in the KSP expressions or any of the equilibrium expressions, you just get to go like this and cross that side off. That's why we call it a modified rice table, rice chart. Now for every time the solid or the silver chloride breaks apart, you're going to get X of the silver, you're going to get X value of the chloride dissolving. So this ends up being X and X, which now can be plugged into the KSP expression, like so. That X goes here, this X goes here, and you end up with, you know, X times X, okay, which is the X squared. And we know this because this is 1 to 1. So it is going to be the X squared version. So is it really necessary to write all of this down? Probably not, but what I do want to see in your free response questions, if you're for KSP ones, I do want to see the reaction and the declaration of the ratio. Okay, so you want to show that part. You want to show your KSP expression, and then you can plug in there. Okay, show your ratio by doing the reaction, show your expression, and then plug in here. Now we plug in here, of course, and we do our KSP value, 1.6 times 10 to the minus 10. So 1.6 times 10 to the minus 10, that equals X squared. And all you have to do is square root both sides, like so, and you can get your X value. The X value is always the molar solubility of the formula unit. All right? So what is our molar solubility of silver chloride at 25 degrees Celsius? Who has that?
It's a very small number.
It is a small number, because the Ksp is really a small number. So square root that. What do we get? Yes, 1.3 times 10 to the minus 5 molar. So we would use this as our gauge for our sig figs. So this would be the molar solubility of silver chloride at 25 degrees Celsius. So that's a really small, tiny amount that actually is going to dissolve. Very, very small, tiny amount. Everybody good with that? Yes, no? All right. So now we're going to do another one, except for looking at it from a different ratio perspective. And then we'll throw in some of the harder stuff. Yay, got it right. Okay, silver phosphate. Silver phosphate. Now once again, I'm just going to set this one up with the modified rice table, although like I said, the expectation, you don't have to put that every time. Once you have your ratios established and you remember your KSPs, you should be good to go. So here, silver phosphate though, I need to know the formula of that. What's the formula of silver phosphate? So I can start my rice table. Because I got to write out the reaction. I definitely need to do that part. What is silver's charge? What is phosphate's charge? How do I write this formula? There you go. Ag3PO4 solid. Good. Now that means we're going to have 3 of the silver ions that form, and we're going to have 1 of the phosphate ions every time that formula unit breaks apart. Now initially, once again, we cross off the solid, don't need it. Solid's not going to be in the K expression because we're really looking at this one to put in our K expression, the E. Starting out with nothing, we're dumping it into a beaker of water, so nothing's dissolved yet. But once it does its dissolution, you're going to have 3 times of the silver dissolving, because every time this formula unit breaks apart, 3 are going to dump in there of the silver. And 1 of the phosphate will dump in there. So we get our 3x and our x here. Writing out our K expression, or KSP expression, we get the concentration of the silver raised to the 3rd times the concentration of the phosphate. And here we go, we plug this in, the 3x and the x. So the 3x to the 3rd times the x, and this is where we're going to get that KSP equals the 27x to the 4th. Now we can plug in, we use our KSP value. Okay, 1.8 times 10 to the minus 18 equals 27x to the 4th. And we need to solve for x here. Now, everybody know how to use their 4th and 5th roots on their calculators, because you need them. If you're not familiar with where this would be, it's under math on the graphing calculators. Mine, it's number 5, and it looks like this, where there's a little x there. And that allows you to change the root on it. So you divide by 27 first, and then do the 4th root of that answer. So what do we get for x? Yes, exactly right. 1.6 times 10 to the minus 5 molar. This is for Ag3PO4. All right, so now we're gonna compare. What do these numbers mean? So we dump a silver phosphate into water. It's gonna dissolve 1.6 times 10 to the 5 moles per liter. That's how much it's gonna dissolve. It reaches equilibrium. It's saturated at this point. Very small amount too. But let's compare it to exercise 1. Going back to exercise 1 and looking at silver chloride. Let's compare. What was the molar solubility of silver chloride? What was its X for silver chloride? 1.3 times 10 to the minus 5, right? This was the molar solubility for the silver chloride. Ksp for silver chloride was 1.6 times 10 to the minus 10, right? So let's compare now, looking at our silver phosphate and our silver chloride. Which one is more soluble out of the two? Which one can dissolve more? Yes, the one that can dissolve more happens to be the silver phosphate. It's just slightly more, 1.6, different than 1.3 here, right? Not very much more soluble, but it is slightly soluble, a little bit more than the silver chloride. So, if you just looked at the KSP of the silver chloride here, and only compared it to the KSP of the silver phosphate up there, and didn't take into account that the ratios of the ions are different, which one would you be likely to say is more soluble? You would say that the silver chloride would be more soluble because the KSP is a lot larger for silver chloride. And this is exactly the reason why you cannot directly compare KSPs of things that have different ions, different ratio of ions. If they are a different ratio of ions, you cannot directly compare it. You have to do the calculation and find the molar solubility, and then you can compare them. Because the molar solubility of the silver phosphate is more, it can dissolve more at its equilibrium than the silver chloride can. So mathematically, that's how this works out. There's a lot of different various things that they use. Like for instance, good question is, how is this applied to, what would you use this for? So say you have like a polluted sample of water that has some heavy metals in it, and you need them, you want to have them precipitate out at different times and collect them separately. Well, you can use their KSPs and figure out which one would precipitate out. You add that particular reactant and it precipitates out faster, then you can filter it. So they do use that, you know, it's called selective precipitation. It is a technique to get different ions out of solution. And like I said, the main one I can think of is for water pollution or things that are contaminated, where you know it has like a contaminated heavy metal in it. You could easily use this technique in order to separate it and clean the water. Does that make sense? Sure.
So the one that's more soluble is the larger number?
Is the KSP, in this case, the larger one, the one that has the higher, the lower KSP actually is more soluble.
Oh, the lower KSP.
Yeah, the lower KSP, this one, 10 to the minus 18, is actually more soluble because the ratio of the ions produce more dissolved substance. But that's because the ratio of the ions are different. So when they're different, you can't directly compare KSPs. When they are the same ratio, you can directly compare KSPs.
So when they're the same, it's the larger KSP.
That will dissolve more.
Yeah.
Yes.
And then you compare their molarities if it's different.
If it's different, you go to molar solubility. Exactly right.
Okay.
All right, so now we get to talk common ion effect. Common ion effect, one of the ions in solution that's in equilibrium is already dissolved there. And basically what happens if you add in a common ion, it's going to shift left towards the reactants, which means it's going to precipitate, or it's going to make or have more solid that won't dissolve, so your solubility decreases if you add a common ion. Common ion effect always makes the solubility decrease. Let's look at an example here. Say we have a beaker where the barium sulfate was dissolved and it's at equilibrium. It's saturated and at equilibrium at this point. Now, gonna take some barium nitrate and add it to this barium sulfate solution already there. In that case, the common ion is going to be the barium. Nobody really cares about the nitrate, but the barium, Ba2+, okay, that is like adding in a product. And we know what happens when you add in a product according to Le Chatelier's principle. What happens? Which direction is it going to go?
Left, right?
Yes, it'll go left towards the reactants. If we're adding in a product, it shifts left towards the reactants. Very good. And you add in a product, that means Qsp is greater than Ksp, because now you've made the products higher, goes left. Now, solubility then is going to decrease because now you have more undissolved solid. So solubility went down. So that's the key thing here. Attached to common ion effect, solubility, molar solubility, it decreases with a common ion. You have to add a common ion to this, the system. In this particular example, the system was set up to be the barium sulfate, this one. It had been dumped in water and it reached equilibrium and was saturated. Then we came along and added in some barium nitrate. Well, that of course means the barium from the nitrate is the common ion. So we added in more barium. We basically added in product, shifts left towards the reactant, so you have precipitation, which is decreasing that solubility. So let's think about our Le Chatelier's lab in our first one where we had the sodium chloride. And we dumped in the hydrochloric acid into there, right? What was the common ion of that one? What was the common ion there? Adding to the sodium chloride, we added in HCl. Yes, it was chloride, because the chloride part of the HCl was being added in. So the common ion would have been the chloride. The chloride, of course, adding that in was adding in product. It shifted left towards the NaCl solid, and that's why you saw the white cloudy stuff in the video or here in the lab. So that one was really caused by the common ion effect. And what we know, the molar solubility of it decreased. All right. Now we're going to move on to working some common ion effect problems. And we're going to look at later on how to do the comparing Qsp, Ksp problems. And we're going to look at things that affect solubility, such as pH, complex ion formation. We already know what the common ion effect does. It decreases solubility. And I think that's pretty much what we're going to do here on this side of the notes. So here, exercise 2, we want to calculate the solubility of the silver chloride, which there's its Ksp 1.6 times 10 to the minus 10. But instead of dumping it in water this time, which is what we did last time, we just put it in regular water, pure water. Here, we're actually going to put it in 100 milliliters of 4 times 10 to the minus 3 molar calcium chloride. So this one's not going into water, this one's going into something that already has a compound in it dissolved. So looking here at this particular one, we're going to set up the rice table. In this one, common ion effect problem, we're going to need a rice table, so set it up. We're looking for the solubility of AgCl, so this is our reaction we're looking at. Now, yes, we don't need this part. Solid doesn't matter, not in part of the expression here. Now, initially, we're dumping it into the calcium chloride 100 milliliter beaker. So no silver is there to start with. However, initially, we have some chloride already present, do we not? We have the chloride that's found in the calcium chloride. It's already present, so we have an initial concentration of the chloride to begin with. Now we need to figure out what that is. What is the initial concentration of our of our chloride here in calcium chloride? What do I need to know about that particular substance before I can figure out the concentration? Concentration should be the same as, like, the volume isn't going to affect the concentration because it's going to be a certain moles per liter. The concentration of the calcium chloride is 4 times 10 to the minus 3. But yes, we need to know in calcium chloride how many ions of chloride are in there. So yes, the idea of looking at this, you don't really have to do a balanced equation. But if you look at the formula there, calcium chloride happens to be CaCl2, because calcium's plus 2 and chloride's minus 1. So what does that mean about our concentration of chloride in there? If it's 4 times 10 to the minus 3 molar calcium chloride, what is the concentration of just the chloride? Because every time one of those calcium chlorides separates, you're going to get 1 calcium and 2 chlorides out of it. So what do we need to do to our concentration here? Yes, we need to double it, right? Because every time this separates, you're going to get 2 of these. So the 4 times 10 to the minus 3 needs to be doubled. That equals 8 times 10 to the minus 3. This is starting out at 8 times 10 to the minus 3. I'm just going to forget the zeros for now. Okay? We'll look at sig figs at the end. All right, so that means when we're dumping the silver chloride in here, that's going to be plus x, but now this is going to be 8 times 10 to the minus 3 plus x. Because we already have an initial amount in there. So now we're filling out for our equilibrium that is going to go into our K expression. Okay, these two values are going to go into our Ksp expression. So let's write that out. Ksp is the silver times the chloride concentrations. That goes here. This one goes here. So we plug that in. And this is 1.6 times 10 to the minus 10. That's the Ksp. It's going to be x times 8 times 10 to the minus 3 plus x. Now, for this particular one, you can do it this way, but I'm going to recommend not in just a minute. You could just stick it into the graphing calculator, and this can be y1, this could be y2. And then you can solve for x. Find the intersection, all that good stuff. That actually takes more time than you really need to do. Because looking at this 1.6 times 10 to the minus 10, Ksp is a really small number. So what do you think the value of x is going to be?
Also very small.
X is going to be really, really, really small too, right? So if we add x to this much larger number here, is it going to matter? A very small negligible amount here added to this 8 times 10 to the minus 3, well, we don't really need to do that because it's not going to change this number. This number, like the significant figure digits on it, is going to fall off. So you get to do something here where you eliminate the x in this particular part of the expression. Why do you get to do that? Because this number is so small that it's not going to actually add in. Okay? So this is negligible. I don't know how to spell that. I think it's this. Negligible. Negligible.
This is negligible.
That does say bile, right? I'm missing a something here. Whatever. So it's basically, here we're going to go with too small. There we go. We'll go with too small. Since I can't spell today. Too small. All right. So, just for those that need the concrete appearance of this, you can go ahead and graph it, and what you would get when you graph it is 2 times 10 to the minus 8. You can check that later. But for those who need the mental idea of why this doesn't need to be added in, let me set it up for you over here. We have 8 times 10 to the minus 3. It would be written like this. You graph it, you would have gotten this number, which is really small, right? So that would be this number. Right? So, the 2 would be here. This part definitely wouldn't be factored in terms of sig figs. It would drop off. So that's why you get to eliminate x in the common ion effect problems, because the amount is so small that it's not going to affect there. It's not, you don't change this one. It's only the one that would add to the much larger number that you get to eliminate. So that's what you see here. Now, another thing I want you to point out to you mathematically why the common ion effect also decreases solubility. Because this is the value, the molar solubility when you add it to the calcium chloride solution. If you compare that to the silver chloride from exercise 1, the molar solubility in pure water for silver chloride, it was 1.3 times 10 to the minus 5 molar. So mathematically, this shows you that the common ion effect actually decreases solubility. Because instead of being able to dissolve 1.3 times 10 to the minus 5, now it can only dissolve 2 times 10 to the minus 8. It does not have the same level of being able to dissolve. Does that make sense?